Hi, welcome to the notes for Mastery Check 12.3, and I hope most of this is going to be a bit of a review at this point. We're starting off with a question here. It is, how does a positive point charge affect the space around it? So here is a rather complicated looking diagram, but I hope it's not too hard, of sort of an overhead view on the bottom, and then kind of like more of a profile view here of a potential hill that's caused by a positive charge. So in my diagram, I've got colored lines. So looking at this one here, these red lines, those are their electric field lines, and notice they have direction. So that if I were to put another positive charge here, maybe I'll pick a different color. If I put a positive charge here, it would experience a force in the direction of those field lines. Looking at the other one, if I were to put a positive charge, maybe that sort of diagram lines up with about here, right? It would experience a force, and we can imagine it's kind of like the hill, and it would experience a force because it would try to roll downhill. If I put that same charge closer together, I could tell that the electric field strength is stronger because those lines are closer together. So again, if I kind of had those lines, shown like this, as I get into this zone over here, those lines are closer together, so I can tell that the field is stronger. So if I put that charge up over there, I can see it's more steep and the field is stronger. The other way of looking at it are in the terms of the equal potential. So those lines here are the concentric circles. So in this case, it looks like the blue, purplish almost, equal potential lines, and here they're circles, and over here they are done by the height. So this height here, it would be the outer circle, this height would be the next circle, and so on. So again, with moving this positive charge from here to here, you can imagine, well, I'm storing energy, because to move it from this location to a higher location like that would take effort, because I would be pushing this to a higher location. So the first thing that we can say is that the charge creates an electric field around it. And so when we put this out here, we end up getting an electric field diagram, a very simple one. I'm only going to put 3 arrows like that. And that also looks similar to the steepness of a hill. So if I put like that, how close these lines are together would be similar to how far up the hill is. The other thing that we can think of is that putting that charge down in space creates an electric potential hill, and we can think of it as the height of a hill. Here I've got some neat little diagrams. This looks a bit more three-dimensional. These two are trying to show the same thing, and these two are showing the same thing too. These are the lines of potential, and this is just like an overhead view, and this is like a neat three-dimensional view. And so when I'm looking at what is electric potential, let me just define these two. So electric field, I'd like to use this E symbol for electric field, and I'm going to say it's the amount of force per charge. And so the units for electric field would be newtons per coulomb. Okay, so the units for electric field, because it's how much force per coulomb. And it has direction, so I'm going to put an arrow over that, reminding me that it is a vector. For electric potential, we use V here, and electric potential is the amount of energy stored in the field. So electric potential energy stored in the field, again, per charge. So the units here would be joules per coulomb. That's kind of cool. So thinking then about elevating a charge. So earlier here I had this positive charge that I'm moving up the hill. So thinking here, when I move a positive charge, here we can say up the hill. What does that look like? Well, I'm moving it from a lower location to a higher location. So what I'm going to be looking at is the change in potential. So not just the potential, but the change in the potential. What was the change in height? So the change in potential is going to be equal to the change in energy divided by the charge. So actually I can solve for this, and I can say, well, how much energy does it take to move this charge up the hill? I can say this is going to be equal to the change in potential multiplied by whatever charge I moved. So let's say if I had like a 10 volt change, if I moved it from 10 to 20, and I was moving 1 coulomb in this case. Again, volts here is the same thing as joules per kilogram, joules per coulomb times 1 coulomb. So this would be, oh, that would take 10 joules of energy to move it. I would have a change in EE. So when we are thinking about change in energy, I'll just remind you, like from our LOL diagrams, that we would have some amount of EE to begin with, and then we would have more EE afterwards. So the change in it would be how much work we did. So we can really say that the work is equal to the change in electric potential energy. How much energy did we put into the field or put into the system? That was how much work we did. If we were looking at the same thing for in terms of the force that we did, if I looked at this force and I said, okay, work, another way to think about work is that it's going to be some force for some distance. And so if it's a constant force, we can just multiply those two together. But it would be a little bit hard to calculate here, because you can see as I'm pushing along, the force increases. It starts out small and it ends up larger. When we are moving something up a hill that's nice in a straight line, if we took this positive charge and we moved it up a uniform strength field that we had in between two charge plates, I could use this idea to think about how much work we've been doing. So you can see this idea of potential is often a little bit easier to solve for questions that are involving work. In the previous worksheet, you did a lot of questions that were similar to this, so I'll just do one example like this. It says here, point P is located at the center, and the first part is, could we draw an electric field at point P? So if the field from 1 is E, so I'm going to say the electric field at point P is going to be equal to, it's going to be equal to the electric field caused by, here I should number these, how about we'll call this one charge 1 and we'll call this one charge 2. So the electric field at point P is going to be equal to the electric field at that point caused by charge 1 plus the electric field at that point caused by charge 2. I'm going to put little arrows on the top here just to remind myself that these have direction. So when I add them, I gotta add them like vectors. I gotta do that tip to tail idea. So just thinking here at point P, if I place an imaginary positive test charge there, I'll say, oh, that would be a repelling force. In other words, the field in this direction is away from positive charge. So this is the electric field at that point caused by charge 1. So in other words, this one here is this arrow, okay? Secondly, the field caused by Q2 at that point, again, would be away. So this would be the field caused by number 2. So if I want to add the two together, what I end up getting is, and I have to do the tip to tail business, is I would go like this, okay? Because it says this is the center, I think it's fair to say that those two are going to be 90 degrees away from each other. This is going to be 90 degrees away from each other. So if this is 1 unit E and this is 1 unit E, then we'd have to use Pythagoras, and I think we end up getting what, the square root of 2 E. So it wouldn't be twice as much. It's not 1 plus 1 isn't always equal to 2 when we're talking about vectors, because we have to think about the direction. So our answer for that one would be the square root of 2 E. So whatever the original one's, the new one's going to be, square root of 2 is about 1.4 times as much. The second part is talking about electric potential. Electric potential is a little bit different, and here I've got this really cool 3D diagram of the same thing. So I'm thinking that, here, let's just see, this point, it's pretty close to the right way. Here's positive 1, here's charge 1, here's charge 2, here's charge 1, here's charge 2, so this one has to be, I would say this would be about where P is, okay? And you'll see that, well, which way was downhill? Like, did we get this direction right? It looks to me like, yeah, the direction, if I placed a ball at that point, which way would it roll? It would roll downhill that way. That would be the direction of the field. That's the direction it would experience a force. But for electric potential is like, what's the height at that location? And it's not 0, because 0 would be like, more way over here at the red zone. So how do we figure out P? Well, if we say that the I'll go back to this, and I'll just erase my old stuff here. If I'd say that the V is how much potential is the height caused by one of them, and again you can think of, so if this is before we put a point down, and then here's after we put a point down. Here, you know what, I'll just try to draw this nice here. Okay, so this is my attempt to draw. Okay, so here's the ground. And when I place a positive charge, like at this location here, then I get this hill, and I'm going to say that this is 1 unit here. So from here to here is 1 V. And so if I place a second charge right close to it, it's like I'm adding to the hill. So there's my second one, my green one. So what happens here? So I've got the potential at that spot caused by the first one, and I got the potential that's caused by, the green positive charge that I put down. What do I do with those two? Well, here's one thing to think about, that electric potential is scalar. I'm just talking about height. I'm not talking about height in some direction. So it's like I've added more sand on the top. So if this one is 1 caused by the blue charge and this is 1 caused by the green charge, this would actually have a height that would be about that tall. So my two added together would end up being kind of going like that. And you can get that sense in here, right? That this is quite high up. You can see how those are added together. So to answer that question, it would be, what would be the value due to the 2 point charges? And the answer would be, well, I'm just adding the two together, so it would be 2V. Okay, we've got one more question here. Okay, and I noticed there was a little bit of a typo here. The electric field can be measured in newtons per coulomb. I like that, but it's not joules per meter. It's volts per meter. Okay, so looking at this, here is the initial situation. These two plates are some distance apart, and now clearly at the final they're farther apart. So I think that we've done enough of those kind of questions where if we just had two charges like that and then we move them farther apart, you would recognize that we would be, well, there's a couple ways to talk about it. They're attracting, and we're going to be, going against that force. So we're going to be moving it against the field. We're going to be storing more energy. So in this case, we would say, there'd be more energy afterwards, right? If they're single charges. And it's the same case here. You just have a bunch of charges all lined up. So I think it's pretty fair to say, because it's taking effort. We're doing work when we are forcing this farther away. So there's going to be more electric potential energy in the final. Right, so we've done positive work, and it says compare the potential difference and the field strength of the initial and final changes. Well, okay, so first of all, between the initial and final, we're saying there more EE. And now we're wondering about potential difference. So we're saying, what about the potential difference? How do you figure out potential difference? Well, potential difference, or change in potential difference in this case, would be the change in EE per charge. Right? This is our definition of what is potential. It's the amount of energy stored per charge. Well, and it's kind of a little bit different way of thinking. We're thinking about this whole situation about how much energy has been stored in the field. Clearly, we've got more energy stored in the field afterwards. So we know that this number here, the numerator, has gotten larger. We've stored more energy afterwards than it had before. What about the Q? Are there more or less charges involved? Well, if I look at it, there's the same number of pluses and minuses, right? So just to write this down, we've got more final EE, but we have the same amount of charge. So what happens when the numerator gets bigger and the denominator stays the same? We're going to say, therefore, or maybe we should switch back to blue, we've got more potential difference. So, I don't know, let's make up some numbers. Let's say that between here and here was a change in potential of 40 volts. So maybe over here, now the change in potential is equal to, well, how much do we move it? Maybe it's 60 volts now. Okay, what does that look like? Well, if we do our hill analogy, between our original, we had this, actually, it's positives on the left-hand side. So that part's higher. So maybe originally it kind of looked like here. So this was the beginning of the hill. That was the end of the hill, and this was an increase of 40 volts. So how much did we change it by? We lifted it 40 volts. And as we moved, move these two apart from each other, let's pretend that the negative one stayed the same and we moved the positive up. So we kind of like took this and we moved it up here, and so now we have a difference of 60 volts. Okay, so you can sort of moving all these charges up the hill, or just stretching them so they're farther apart. Okay, you can move both of them at the same time. And you'll notice in my way of talking about this, it's still this same slope, right? It's still that same steepness altogether. So that helps us with the last one where it says, and what happens to the field strength. So, and actually I'll tell you that the field strength which we, electric field strength, I used to do that, stays the same. So it's kind of like this is still the same slope. Okay. One other thing that it's interesting that also happens if I had that difference of potential maintained by a battery. So let's just say I had two plates here, right? And let's say this is a 9-volt battery, and this is the plus side, and that's the minus side, and then I took those two plates and I still connected it to that same 9-volt battery. Right? It's the 9-volt battery that determines the potential difference. So in this different case here, what's the potential difference between like the positive side and the negative side? It's 9 volts, right? It's the potential difference of 9 volts. This is 9 volts higher than that side. Even though I've moved these things, then these is still going to be, the potential difference is going to be equal to 9 volts. It's a little bit different because here the battery is the thing that's creating that difference of potential. So in fact, I think what might happen is that the concentration of pluses and minuses will be different. And again, now you can think about what happens to the electric field. Well, the drop here, so electric field, just a reminder, electric field is in newtons per coulomb, but it's also in volts per meter. So here it has a drop of 9 volts, and maybe it was over 1 meter. Here it could be a drop of 9 volts. It could be in 2 meters. So you can see that if it's connected to a battery, the potential difference is going to stay the same, but the strength of the field is going to decrease, because the strength of the field is going to be, well, how much did it drop divided by how far apart are those plates, because you can think of this as volts per meter. Maybe I'll use D for distance here between the plates, and volts per meter. So I hope that helps a little bit. All right. And as always, I will see you in class.